Hello, everyone. Thanks a lot for coming to my talk. My name is Pau, and I'm going to be explaining how to build an augmented reality application with Compose and OpenGL. Brief introduction about myself. I've been a software engineer for about 12 years. I'm originally from Barcelona, Spain, and I moved to southern Germany in Stuttgart when I joined TeamViewer 5 years ago. In addition to the remote control functionality that most of you might know from TeamViewer, we also have use cases for the frontline worker, and more specifically, where I've worked on the TeamViewer SysAR application, where we use a SysAR to cover the use case of having a remote expert help you fix a real-world problem in the world. So I'm sure many of you are quite familiar and probably very experienced with Compose. But how many of you have done something with OpenGL before? Quick show of hands. OK. Keep your hands up if you have been successful at it, if you consider that you were successful at that. OK, less hands, but still a few. Good. So one of the motivations that I had for this talk was that I've seen over the years people asking on Stack Overflow, how do I render a line from point A to point B with AR Core? How do I render this, or how do I render that with AR Core? So it became obvious to me that the separation of what AR Core does and the actual rendering was not clear enough. And now that we have Compose, I thought it was a good opportunity to see how we can combine these three. So we will learn the tools that we have available to do 3D graphics, and we will understand how an augmented reality experience is not that different from any other virtual experience. Oops. Yeah. That said, I want to make clear that this talk is purely for educational purposes. I'm not here to sell you any specific framework, but more to talk about how things are done under the hood. I've created a sample project, which is available on GitHub. I will put the link at the end of the presentation. And feel free to use that code in your own application if you want. Just be aware that the code might not be production ready, so test it beforehand. Also, when talking about AR, there are many different use cases that we can implement, and I'm going to focus mainly on using the rear camera of the device, so focusing on what you see in front of you instead of things like applying filter to your own face or other use cases. And as you might know, on Android, we use the OpenGL ES, the embedded systems version of OpenGL, but for the sake of simplicity, I'll just say OpenGL for the rest of the talk. OK, so how can we combine OpenGL rendering with Compose? On Android, if we want to render OpenGL, we have to do it on something that's called a surface. And the Android UI framework provides us with these two classes to get a surface, the surface view and the texture view. Both of them only give us this surface, and we have to interact with the EGL library to get the EGL context and the EGL surface, and usually also handle the render thread. You can also render on the main thread, but it's usually not recommended. You might also know that there's the GL surface view since API level 3, so a very long time ago, that basically extends from the surface view and provides us with that EGL surface and EGL context already handled. It gives us a render thread, and we're ready to start rendering OpenGL graphics. So from Compose, we still need to use one of these. Thankfully, the engineers at Compose created the Android view, as you might know, to use any view from the traditional UI toolkit. And we can use an Android view, create a custom composable on top of it, and use one of these three. Recently, Compose Foundation 1.6 released these two composables, Android external surface and Android embedded external surface. We'll see the source code in a second, but I can already tell you that was too fast, that they internally also use an Android view to wrap correspondingly a surface view and a texture view. So at the end, the main difference, we still have to choose between a surface view and a texture view. And the main difference is that a surface view creates a hole in the view hierarchy, and the GL content is put either behind or in front. Texture view was created to cover some use cases that surface view was not ready for, and those use cases are to interlace the GL content between other view elements, and with that, maybe apply some transparency. Let's quickly check some code. In this sample I've prepared, this would be one way of implementing this custom composable with using the GL surface view. So we have the Android view, and internally it creates a surface view. If you have ever worked with the GL surface view, you might be familiar with the calls to set EGL context factory, set EGL config chooser, and finally set renderer. I've built a couple of things around for this project, but it shouldn't be too difficult also to do things like properly handling the life cycle of the renderer, since you're all Compose experts. Let's check out the code from Compose Foundation. We can see as I was saying, the Android external surface that does exactly that, just now with a surface view. So using an Android view to wrap a surface view. And if we go down to the Android embedded external surface, again, it's using an Android view to create internally a texture view. For the rest of the talk and for this project, I stuck to this custom composable I've created. You can use any option that I've presented, and as long as you can handle the EGL contents and all of that, feel free to go with that. To use this in a real application, then it's just as easy as any other composable. You add it into your Compose hierarchy, and here I have created the render and made the OpenGL view full screen. This render, which is defined down here, only changes the background color. As you can see in the preview, here just gray. On the Android Studio, the preview doesn't know what the GL content is going to be. So let's quickly execute that on the device. I have my running device here with this sample app. And if I execute that, we have now this full screen OpenGL view, just changing the background color. Very exciting, huh? Let's move on. We now know how to use OpenGL from Compose. So I've prepared now a bit of a crash course of OpenGL. Unfortunately, we don't have enough time to go in details, but there are many resources online. If you're interested, come talk to me later. I can point you to a couple of online resources. But I prepared here a few things that I believe sometimes are a bit confusing. And the first one is that OpenGL is just an API to a rasterizer. And what that really means is that its main job is to transform 3D data into a 2D representation, which is an image that will end up in your display. I'm going to rephrase that a bit. We're passing 3D data to OpenGL, and that data is going to be transformed to create that 2D representation. I'm saying that because OpenGL doesn't know the concept of a 3D scene, a 3D mesh, or a virtual camera. It's all up to us. And then all of these transformations are done through what's called the graphics pipeline, which is a process of very well-defined stages. One runs after the other. And some of them can be configured, and some of them have to be configured. We have to pass code. We have to pass programs to the GPU, and it will be executed at different stages. Those programs are called shaders. Probably you already heard about shaders. I won't go into too many details in shaders. More, I'm going to explain what their goal is. So at the end of the day, what we want from the CPU is to submit some commands and to end up seeing something on the display. Every time we submit one of these drawing commands, we go through this graphics pipeline. We're passing this vertex data. That's the 3D data that I mentioned. And then we start with this vertex shader, which is one of these programs executed on the GPU that it's executed in parallel for every vertex separately. And its job is to transform that 3D data into a coordinate system that OpenGL expects. Then there's shape assembly and the geometry shader, which combined are in charge of generating that geometry out of the vertices. Then there's the rasterization, which is the process of dividing each triangle into fragments. And you can think of fragments as pixels, but there isn't usually, or there isn't always a relationship one-to-one. We might have more fragments than pixels or less fragments than pixels, depends on the situation. Then there's the fragment shader. That's the other fragment that we have to configure. And it's also executed in parallel for every fragment. And its job is to output, to decide which color that fragment will have. Then there are some tests executed and some blending operations, and the result goes to the output, to the color buffer, and finally to the display. I put here in parentheses the word frame buffer. We'll get into that a bit later. Just remind that there's something called frame buffer. So from the graphics pipeline, I want to focus now on specifically, I was too fast, on the vertex shader. As I said, we're passing this 3D data to the vertex shader, and we have to transform that data to the coordinate system that OpenGL expects. And what OpenGL expects is what's called clip space, also normalized device coordinates, NDC. And it's this cube, it's a mathematical cube. It goes from -1 to +1 in the 3 axes. And we always have this cube, this clip space. It's always this, no matter the shape or aspect ratio of your view, even if you're in landscape or in portrait, it's always a mathematical cube. And the whole point is that any vertex or geometry that falls outside of this clip space will be clipped, will be discarded. It won't go into display. Everything that you see in screen then has been inside this cube. I'm explaining all of this because, again, OpenGL doesn't know the concept of a virtual camera. When you're playing a video game, you have a virtual camera that's moving around the world. OpenGL doesn't know that. We pass that information. We pass the information of the virtual camera, our 3D mesh, and we transform that data. But we don't necessarily need to do that. We could directly use clip space. We'll get to that a bit later. So knowing all of that and working with the OpenGL API, one would then build a first rendering engine, which would usually consist of having an easy way to render objects, usually with textures. Then we would have this virtual camera that would contain a view matrix and a projection matrix, and some type of scene graph. Could be as simple as hard-coded objects or a very complex graph representing your scene. Let's quickly go back to the sample. Again, I have a sample with a full screen GL view, and on top of that, another composable that adds these arrows that will allow me to control the camera. Down here, this is one of the cases where I have a very simple scene graph, just some hard-coded objects with some hard-coded coordinates. And again, the preview, the GL content is gray, so from now on, I'm not going to show the preview anymore. Let's see that running on the device. And we have a virtual scene, hopefully more exciting than the one before. And we can navigate this scene with these arrows. So here you can already imagine what's happening. We're sending this 3D data to OpenGL. And there's all these transformations happening. And the cubes that we don't see fell out of clip space. The ones that we see are in clip space and therefore continued in the graphics pipeline. Oops. Okay. So our goal here is to build an augmented reality experience. So far, we only have a virtual experience. How do we go from here to augmented? What's the missing component that we have? What's the component that we're missing right now? Well, if we want to augment reality, we need to see reality. We need to see the real world. And for that, we need then to see, we need to render the camera image. Let's take a quick detour to see how we can do that. That's one of the cases where I said we can pass coordinates directly in clip space. We don't need to pass 3D mesh that it's in some position in a virtual world and a camera object. So we can directly create a quad, a plane, in this 3D clip space. And from there, we can render this piece of geometry, and using texture coordinates, we will then be able to render the camera image. Going back to the sample project, again, our full screen OpenGL view, on top of it, another composable to handle the camera permissions. You might be familiar with all of that. And if we go to the render function of this renderer, we are first rendering this camera image. At this point, again, all the graphics pipeline is executed for that 2D quad. And on top of it, I render our virtual object. Here is the piece that is in charge of updating the geometry of that camera image. As you can see, it's just 2D coordinates. The Z will be automatically 0. And it's coordinates in clip space from -1 to +1 to fill the clip space, because in this case, I wanted to render the camera image full screen. This call here comes from AirCore, and what it does, it gives us the correct texture coordinates to correctly map the camera image to the current orientation of the device. As you might know, the camera sensor is rotated in one specific direction, but maybe your device is in portrait, is in landscape, so all of that needs to be handled. AirCore does that for us. Let's run this sample, and we can see now our virtual scene on top of this background image, which is our camera image. So things are getting more interesting. Now we're a step a bit closer. Now we see the real world. So the question would be, is this AR though? Quick show of hands. How many of you think this is AR? Some hands? It's easy to argue that this is not AR yet. And the reason for that is that we're not using any context of the real world yet. We just have something floating, just an overlay on top of it. And similar to the sample on the left side with the arrow controls, what we need is a way to move our virtual camera in this virtual world with the same movement that our real world device is moving. And that's where AirCore comes to the rescue. AirCore has basically two roles. One of them being tracking the position of the mobile device as it moves. And that's exactly that. As AirCore keeps track of the position of the device, it can give us now the camera view matrix and projection matrix. So we're going to take the sample from before, exactly the same sample, and just up here, after updating AirCore, I'm going to update the camera position. Let's quickly check the code of this function. It's not that long, 3 lines. We get the camera object from AirCore, then we get the view matrix, and we set it to our virtual camera. Then we get the projection matrix, and we set it to our virtual camera. If we execute this sample now, we can see how, after a few seconds that AirCore initializes, we have now something that resembles augmented reality, or definitely, probably many of you would say that now that is augmented reality. So if there's one thing that you're going to remember from this talk today, I want it to be this one. An augmented reality is a lot of things. There's a lot of things under the hood, but in terms of rendering, it's nothing more than a virtual experience with a background image and a virtual scene in front of it. And that the virtual camera view matrix and projection matrix are updated according to the real-world device. Moving forward with the second responsibility of ARCore is environmental understanding. As you navigate the real world, ARCore tries to understand better, analyzes the world in front of you, and it's looking for things they can track, trackables. It starts by detecting feature points or very distinctive points where they can track over time, and then with that they form planes. And as ARCore keeps updating its understanding of the real world, the virtual world origin might change. And that's very important also because different ARCore sessions will have different world coordinates. You might start an ARCore session pointing that way, and in this case, the virtual world coordinate system might point in that direction, but if now you start an ARCore session in that direction, then it's completely the opposite. So we need a way to have our virtual objects stay at the physical location, and we can do that by using anchors. We can create anchors through the ARCore session or doing a heat test. And basically with anchors, we're asking ARCore, please remember that physical location. And the way it works is that even if the world origin changes for some reason, the anchor will update its relative position to that new real world origin. And if we place our virtual object relative to that anchor, then our virtual objects will just stay there. Let's move forward, going to more advanced topics. Back in 2020, ARCore released the Depth API, and it was defined as understanding the size and shape of real objects in a scene. It creates depth images or depth maps, thereby adding a layer of realism. There's first point here, understands the size and shape of real objects in a scene. When we do one of those heat tests to create an anchor, now also not only we can use feature points and planes, we can now also use depth points, which tend to be more accurate. But then the second part creates depth maps. Google posted these two examples. On the left side, you can see the depth map visualization, which every different color represents a different distance from your device. And then on the right side, you can see this CAD. On the left side, it's not using any of that depth information, but on the right side, they added occlusion. And occlusion really means hiding a virtual object behind a real-world object. And the way this works is that given that we know per pixel the distance to our device, let's say you're pointing in this direction and the real-world object that you're seeing is 5 meters away from you. But then we also know all the information from our virtual scene, and maybe a fragment falls a bit farther away, let's say 10 meters. So from this point of view, we shouldn't see the virtual object. And we have that information, so in the fragment shader, we can compare those distances and we can know this is farther away, then we can discard it. Or we can apply some opacity or something like that. This way, creating this illusion of occlusion. It's still, if you think about it, a background image and a virtual object on top of it, just that we don't see parts of it. We can apply occlusion separately to each of the virtual objects, or we can find a way to combine everything together and apply it only once. We'll see that. We will see how to do that in a second. But again, here it's also we need to take into account that transformation for the camera sensor and all of that. Thankfully, ARCore provides that function that I mentioned before to help there. Last year, AirCore released electronic image stabilization, which helps to reduce camera shake in videos. It works by detecting small movements in the camera and then compensating for them by shifting the image being displayed. By shifting the image being displayed. When I read that, I thought, well, I know how to render the camera image. I have a 2D quad in clip space. And then I only get the texture coordinates needed, and that's it. Turns out it was a bit more complicated than that. With this shifting the image being displayed, now what we get is 3D coordinates for our, not anymore 2D quad, now 3D quad. So we get this plane, this shifting. It's not just the texture coordinates adjusting, but we get this plane that might be a bit tilted to one side or another side, depending on the device movement. So when I started working on it, I thought, well, now it's getting a bit complicated if we want to apply occlusion to all the different objects and have this transformation done again and again. And I thought, well, maybe there's a way to simplify this. Maybe I can go back from this 3D quad back again to a 2D quad. Let me introduce you to frame buffers, our advanced section of this OpenGL crash course. And you might remember, hopefully, from earlier when I described the graphics pipeline, that everything goes to a frame buffer. And a frame buffer is defined as a collection of buffers that can be used as the destination for rendering. There are two types: the default frame buffer, which is provided by the OpenGL context, and user-created frame buffers called FBOs. Well, that may be a lot. Let's dissect this part. I like to focus on these two parts of this text: user-created frame buffer and destination for rendering. That already tells us that we, as users of OpenGL, we can create frame buffers, and we can use them as destination for rendering. Whatever that means, we'll get to that. And for the sake of completeness, a frame buffer is a collection of buffers. It might be composed by color buffer, depth buffer, and stencil buffer. We're going to focus only on the color buffer today. So let's see how we would use a frame buffer as a destination for rendering. As I said before, usually what we want is from the CPU, submit some drawing commands to end up seeing something on the display. But now, instead of rendering directly on the display, we're going to render on a frame buffer. I like to think of frame buffers as a different sheet of paper, different canvas, where we're rendering there, we're painting there, and then we can use that information somehow. So in this case, we're using a frame buffer to render our scene. But maybe we can render our scene to a separate frame buffer, maybe from a different point of view, maybe the point of view of a light source. And we don't need to output the color of the object, maybe only the distance to that light source. And this way we can create a dynamic shadow map. If you're into gaming, maybe you're following. And the thing is, we can have as many frame buffers as we want, as long as you have enough memory. And that each frame buffer can have a different size. You're not forced to have frame buffers the size of your display. That's one of those situations where you might have more fragments than pixels on the display, for instance, or less. So after that, well, we still don't have anything on the display, so maybe we're missing a step here. Now we can render on the display on the default frame buffer, and we can use that information from our frame buffers that we have generated. We can read those textures, these color textures, and we can use that to maybe create a scene with shadows and some post-processing on top of it. So how can we combine these frame buffers with depth API and image stabilization? This is one example of how one could implement it. You can do it in other ways. And first, we could render our full virtual scene on a frame buffer. Let's call it frame buffer virtual scene. And then we can render the depth map on a separate frame buffer, adjusting for those 3D coordinates that image stabilization gives us. This way, we're doing that transformation from the 3D quad back to a 2D quad. The next step, we can render the camera feed on the default frame buffer. And finally, we can combine our virtual scene frame buffer and the information that we have now in this normalized depth frame buffer. Again, to the default frame buffer. Note that at this point, we don't have anything yet on the display. We've been rendering only on a frame buffer, still the default frame buffer. We've been only changing the contents of the color buffer. Only at the end of the frame, when the call to swap buffers, if you've ever heard of it, then the whole content is put on the display. Let's quickly see that in the sample app again. Here, this renderer implements this process I just mentioned. So as a first render pass, rendering the 3D scene on a virtual frame buffer, or a frame buffer called virtual scene. Then as a second step, we render the depth map, normalizing or transforming, simplifying those 3D coordinates that we got from image stabilization, and now we get simpler texture that we can more easily sample from. And finally, now on the default frame buffer, the display, we can render the camera image, same as we've done earlier, and we can combine those virtual scene frame buffer and depth frame buffer, applying occlusion and image stabilization at the same time. Let's execute that on the sample app. You can see how I can place now, I have heat test here, and I can place some more of those nice cubes, and they're hiding behind a real world object. Not sure how well it's visible up there, but maybe my hands are shaking a bit. So if I enable image stabilization, probably should see now that it's much more stable, and everything works just fine. You can see sometimes some artifacts with occlusion, and that's because AR core depends a lot on the environment in front of you. So if you get very dark areas, like in this case behind this, or very shiny surfaces, the depth, it's more difficult to calculate the depth. So still you might get some artifacts sometimes, but it works pretty well. Let's go back to the slides. Just finalizing now. As a side note, if you've ever heard of the OpenXR standard, it's gaining popularity in the recent years, especially with all the different VR headsets and the Web AR standard, Web XR standard. It's very cool that we have a standard to support these use cases, but it works slightly different. Due to privacy reasons, they say they don't provide the camera image to the application. And so the way it works is that you, as the application, have to render your scene on a frame buffer or multiple frame buffers, and then provide that to the framework. And it's the framework who makes that composition. But still, at the end, it's going to be camera image as the background and your virtual scene on top of it. Quick recap. We've seen how to integrate OpenGL with Compose. We've seen how we can create our custom composable to use a good old GL surface view or one of the new Android external surface or Android embed external surface. If you're ready to deal with EGL context in EGL surface. It's not that complicated, actually. You do it once and forget about it, but it's a bit more work. And then also we've seen that it's preferable to use a surface view. On the other side, we've seen how AR Core does a lot of this heavy lifting, but it doesn't really do any of the rendering. AR Core gives us the data, for us to do the rendering and create that AR experience. And we can do that with OpenGL. And we've seen how those AR experiences are not that different from other virtual experiences, and we're using the same techniques, such as frame buffers, that we can use for off-screen rendering, maybe to simplify processes or to do some post-processing, for instance. And with that, thank you all for coming to my talk. Here's the link to GitHub with all this sample project. I have also added this QR code. I would like to get feedback on this talk, so if you can spend 30 seconds, I would really appreciate it. And yeah, thank you all. I will take any questions you might have.